Okay, so welcome back, everyone. So today it's my pleasure to welcome Oussama Zekri, who will be talking about large language models as Markov chains. Yeah, thank you, Oussama.
Yeah, thank you for inviting me. Thank you for the introduction. So yeah, today we'll talk about our recent work. So large language models as Markov chain in this machine learning and dynamical system seminar. So the first part of the title, large language model refer to machine learning, and the second part, dynamical systems. So I think we're in the theme. So yeah, basically this work was done during an internship at Huawei Paris with my colleagues, so Ambroise and Abdelhakim, PhD student there, and Linus, Nicolas, and Yevgen. So I thank them for this work. Let's first talk about the first part of the title, so large language model. So basically, I will not teach you the fact that those models are really impressive, but I just want to emphasize on a certain point, on a certain emerging capabilities of those large language models. So in 2020, there was this paper from OpenAI that just established the fact that those models can just learn additional patterns during inference in a few-shot manner or in a zero-shot manner. For example, you have this paper, LLM time, where you can input a time series into an LLM by tokenizing this time series. The LLM can just learn how to forecast this time series in a few shot, in a zero shot or in a few shot manner. Right, and more recently, there is this paper from Liu et al. Where they just realized that if you put a dynamical system as an input of an LLM, the LLM is able to forecast or to understand, more importantly, the dynamics of the dynamical system in a probabilistic manner, in a probabilistic way. So yeah, you have those emerging capabilities, but the problem is that those emerging capabilities are really poorly understood theoretically. And there are many problems, many open problems in the literature. For example, here in this last paper, you can see that there is a kind of curve, there is a kind of law, scaling law. We don't have any theoretical insight. So our goal in this work and in this talk is to basically derive theoretical insight on those emerging capabilities. Yeah, so just to recap a bit about large language models. So the idea, basically we build large language models by taking certain modelization of language called autoregressive modeling, where the goal is basically to just predict the next word based on previous one. So for example, if you have a sentence like this, if you want to predict the word danger, you will just use the previous word as a context to do your prediction, your probabilistic prediction. So in a mathematical way, this means that given a sequence of words or a sequence of tokens, you have to compute this joint probability. But doing this is a bit hard, and the autoregressive modeling of language is the fact that you can use a chain rule to write this joint probability as a product of n probability, right? So basically you have now just a product of conditional probabilities, and there are two main advantages. The first one is that with autoregressive modeling, you are putting a kind of order in the sentence, so x1, then x2, then xn minus 1, which is really natural for a language application. And also, this is really a scalable approach, because computing this conditional probability is really easy in contrast to this joint probability, and you just have to do a multiplication basically. So this will be cheap, this will be scalable, and that's why with this modelization of language we can construct those models. So yeah, we have many kind of models to do this, and the best approach so far is the generative transformer. So this is a kind of model. This is a kind of neural network. Like you have this neural network. If you have enough data, if you have enough time, and if you have enough compute, you can just train the right part of this model and build your language model, like for ChatGPT, for example, or one of his cousin, I don't know. So the idea is that our goal is, to just formalize this. So with this aim in mind, I will just introduce some parameters related to this model. So you know that these models, they take a kind of vocabulary space of size t. So this is the word or the token that you will consider, that you will train your model on, and it has a fixed size t. Also, you have another mechanism called the context window that I will just explain in the next slide. And don't forget that this model is a neural network, so you have a trainable parameter set, and you just train the model, and then you have your model. So just to give you some numbers, the number of words in the vocabulary of GPT-3 is something like 50,000. The context window that we'll explain just in the next slide, something like 2,000, and you have this huge number of parameter, 175 billion parameter. In this pretty old LLM, you know that now we have a newer version with basically this number scaled up. Right, so about the context window, just a quick recap. So basically, when you have your model and you will input a sequence, for example, let's say at the top of this slide, a sequence of length 4, you have x1, x2, x3, and x4, which are words or tokens. So you have this sequence, and let's say that your model has a context window of length 7. So when you will input this to the model will output a probabilistic prediction, right, to the sequence, and it will just process the sequence. But what happens if you input the sequence of a length greater than or equal to the context length? So, for example, a sequence of length 10. The model will just forget the beginning of the sentence. He will forget the first token, the first word, and it will just produce, a probabilistic output just by considering the last word of the sentence. And this is really important. This is really specific to the transformer architecture. With this architecture, you have this fixed number k, and like you cannot produce probabilistic outputs if you have sequence with a length more than greater than equal k, right? So it was just a quick recap about context window. And then let's talk about the second part of the title. So just introduce some background on Markov chains. So we will consider the most simplest case of Markov chains. So finite state space, discrete state space, and finite time. So basically this means that your Markov chain can take, so your dynamical system can take value on a discrete space with a finite number of value and in discrete time. So with a more mathematical definition, a Markov chain is just this sequence of random variable where the observation only depends on the previous one. What does it mean? It means that if you have a sequence of variables z0, zn minus 1, zn, and zn plus 1, if you compute this conditional probability, the result will be the same as if you just have the last the last item of the sequence. So this is what we call a Markov chain. And what you can also do is that you can, because of this property, you can just view a Markov chain as a matrix, where the coefficient of the matrix are just the probability of transitioning from one state X to another state Y, right? So to just basic recap, Markov chains. But now we can try to answer the question: are LLMs Markov chain? Because yeah, if we take our previous example, so so you want to predict the word danger with this context. If the prediction of the word danger depends only on the word D, obviously not, because we just explained that the LLM doesn't work like this. So if you look at the token level, your LLM is clearly not a Markov chain, right? But if you see this probability prediction as the prediction between the sequence of token I am the danger and the sequence of token I am there is something to be done, because yeah, by just changing the state space, instead of considering the tokens, you can just consider all the sequence of tokens that you can construct. So the question now is, will it really define finite state-based Markov chain? Because you can imagine that there is a huge number of sequences that you can construct, right? Maybe infinite. And the answer is yes, because you have the finite context window. Remember, just before we said that the model will just view all the sequence of length greater than k as sequence of length k. So basically, you can just consider as a state space the set of all sequence consisting of element of the vocabulary space up to k elements, right? And by doing this, you are able to like listing all the transition probability that an LLM is able to do. So you have this kind of huge Markov chain, this huge matrix representation, with each row represent a state, which means basically a sequence of words. For example, you have the sequence I am a. So the sequence of 3 words can be mapped to another sequence of 4 words. So this is how like the model will do. And it is how the generation step, one generation step will happen. So yeah, for example, you start from I am a, and you will predict I am a danger with this probability, right? But what is okay? This Markov chain, like the size of this matrix is finite, but what is the value of this of the size of this state space? So by simple calculus, you can derive that the value of the state, the size of the state space is this number, which is basically something like 10 to the power 10,000 for just GPT-3. So yeah, as you can see, it is exponential in the context window. And maybe you know that the number of atoms in the universe is something like 10 to the power 80. So this number is just ridiculously enormous. Like it's ridiculously huge number, but this is a finite number. And this is what is important. Like, okay, this is huge, but it is finite. And you know, in mathematics, when you deal with finite objects and when you deal with infinite object, things happen differently, right? So because of this, of the fact that this number is finite, you can derive inside. But what you can't do is that, yeah, you just can't store this enormous matrix. It's impossible. Like we don't have the technology to do it. Maybe in another alliance, maybe they have it, but we don't have it. So the idea is that you cannot really store this matrix. But what you can do is that, okay, if you have your model weights, if you have a few GPU with you, you can access to the row to any row of this matrix with just a forward pass by just prompting the row you want, basically. And you know, this kind of thing, you can put this USB key in your pocket. So yeah, this is possible by just having the model weights in some storage like this. But you will never be able to plot this matrix. But what is really important, as I just said, is that you have a connection to the theory of finite Markov chain, and you can derive insights from it, even if the state space is ridiculously enormous. Right? So okay, I just said that we were not able to plot this matrix or to play with this whole matrix, but let's do it anyway with a toy example. Okay, so you will just consider a baby LLM, what I call a baby LLM, which will consist on a vocabulary space of 2 tokens, 0 and 1, for example, parameter space, some parameter. So this is basically just transformer. So yeah, so you have two number in your vocabulary space, and you consider a context window of 3. If you do this, the state space is just 14. So you can do things with this matrix. You can plot this, and in particular, you can do matrix multiplication. You can do matrix multiplication, and by doing this, you can view the generation step of an LLM as just a matrix multiplication, and then you sample on the output distribution, and by sampling this, you have your next token. Okay, so okay, we will keep this toy example to derive our first theoretical results on LLMs, which we did about stationary distribution. So if you are not really familiar with it, this is something related to Markov chain theory. And basically a stationary distribution just represents the long-term behavior of a Markov chain. It means that, okay, if you generate a lot of time with a Markov chain, this will tend to a stationary distribution in the sense that when you will do another multiplication, you will just have the same distribution vector. And the cool thing with Markov chain is that you can see n-step generation are just the power n of the matrix, right? And basically this matrix will just tend to stationary distribution when n tends to infinity, okay? And the cool thing is that if you have a finite Markov chain, you are sure that a stationary distribution exists, and you are sure that the stationary distribution is unique. So you are sure that your LLM has a unique stationary distribution. This exists, and this could explain one part of what we call model collapse, right? So the idea is that at some point of generation, you will just be stuck in some state, and yeah, you will just do the same prediction. You perhaps with all the instance of GPT, for example, GPT-3, you may have experienced this. So what we derive also in the paper is the fact that we have an explicit convergence rate to this stationary distribution. So yeah, this rate is like exponential. This is an exponential version, but you know the number here is really close to 1. So it means that it can take a lot of time to converge to a stationary distribution. And also this number epsilon depends on the temperature of the transformer. So I don't know if you know what's the temperature, but basically this is this is a parameter that you can play with when you prompt your LLM. And the more temperature is high, the more you will have the diverse output. So basically, we also show that the more you increase the temperature, the more this parameter is higher. So the more it will tends quickly to the stationary distribution. And yeah, I encourage you to just go to ChatGPT, play with the temperature, and you will see. All right. So yeah, this was for the first theoretical insight that we derived thanks to the Markov chain theory, this idea of stationary distribution, and it's linked to model collapse and all this stuff like that. So so now another contribution that we have done is that okay, we have we can write an LLM as a Markov chain. So and we have generalization bound on Markov chains in the Markov chain theory. So can we use this to derive generalization bound for LLMs, right? So the kind of idea, the kind of question that we want to answer in learning theory when dealing with this is that, okay, how much training data do I need for my LLM, for my Markov chain matrix, for my LLM Markov chain matrix to be close to some reference matrix? So to be close to some reference matrix of the language or something like this. And basically this means that, okay, how much data do I need to have a good test error, right? If you prompt your LLM to unseen data, how much training data do I need, right? So what we call sample complexity is exactly the number of sequence that you need to be epsilon class in terms of distance. And this number is dependent on the model parameter, right? So yeah, basically this is, so this number n star is what we call sample complexity. And if you have more training data than this number, you are sure to be epsilon close to some test data or some reference data, unseen data. Okay, so let's try to do it. So yeah, the question now is, okay, how far our matrix in terms of distance is from this reference matrix. So you know that, yeah, for example, for GPT-3, they just train the model on just 10 to the power 11 tokens. But you know, just the number of non-zero elements in the matrix that I showed you is this enormous number, right? So with just this really small supervision, you can. So what we observe in practice is that, okay, the LLM is really impressive and it seems to generalize. So yeah, it asks a question, okay, like let's look at this problem as a generation problem in terms of learning theory. So the idea is that you define a training error, so an error that you have where that depends on like your training data, and a test error that depends on some unseen data. And the goal of this generation problem is just to bound the difference between these two terms. And if your model generalize well, this ARG is just 0. Okay, so what we have done to derive a result on this is that we have done a really light assumption, an assumption that is not done in the literature. In the literature, they are like, okay, we have random variables, and those random variables are independent. And in our case, we said, okay, no, we will not do this this assumption. We'll do a more general assumption. We have some dependency between the training data, and this dependency is expressed through what we call a coupling matrix, Martian coupling matrix, gamma, right? And also you have a term B that depend on basically all the model parameters. So embedding dimension, number of heads, transformer layer norms, etc. And by doing this assumption, you can derive this kind of generalization bound. So with high probability, you have something like this. So the norm of the coupling matrix, which is just 1 in the case of independent random variable, but when the variable are really correlated, this number can increase. So it showed that there is a kind of like it increases the complexity of the bound. You have this term with all the parameters inside, and you have this classical denominator in square root of n, which means that, okay, if you have n that tends to infinity, of course you will have a average generalization error that is 0. But yeah, basically it decreases as 1 over the square root of n. as usual in this kind of generation model results, right? And we just plotted this bound. So in purple here. So okay, we don't really plot this bound, but the sample complexity from that come from this bound, and so in purple, and you can see that if you consider like the number of training tokens of GPT-3, which is something like which is like this, it really it can explain, okay, this is why those models are able to generalize, because you can see that our range of sample complexity, if you increase the tolerance of your distance between matrix, it performs like that. So we can say, okay, GPT-3 has this kind of tolerance between 10 to the power -3 and yeah, so in this range. So this is quite cool to say that, okay, you derive a theoretical bound, and when you verify it on real models, it is coherent. So that was a really cool thing to notice. All right. Then another last contribution that we have done is about in-context learning, and you remember the problem that I mentioned in the first slide, the fact that you have emerging capabilities, but you don't know how to explain them theoretically. So the idea is that, okay, we leverage another time the fact that an LLM is a Markov chain to derive insight on it. So I will just talk about in-context learning a bit. So you know that in-context learning, this kind of emerging capabilities, like when you prompt your LLM, it is able to learn some patterns, something like that. For example, in this table, you have the fact that you have the country Turkey, you have the baklava, the pastry. Then you put France and you put croissant also. And if you put Japan, like the model will understand that, okay, this is a kind of pastry, so I will just associate with the country and it will output mochi, right? So this was for natural language, but if you take a look, for example, at the task of learning dynamical systems, the idea is that you can just prompt the model with the successive value of the dynamical system, and it will try to output the value of the next the value of the next iteration of the dynamical system. So we will take a look at this kind of in-context learning on dynamical system, because we will check if our bounds are tight, and this will not be as costly as pre-training, because you can do this just by doing inference. And also, if you do this and if you control your dynamical system, if you know some things about your dynamical system, you have access to this ground truth, and you will be able to plot the test error. You'll be able to plot it and to check, okay, it has the same same behavior as the bound, right? All right, so the task we considered, but the task of doing learning of a Markov chain. So the idea is that, okay, you want to learn the probability, the transition probability of a Markov chains, but you don't know them. You just know one sample from this Markov chain, from this distribution. You just know you just have access to one sample drawn according to this distribution, drawn from this distribution. So a classical approach is this frequentist approach. So the idea is that, okay, you have your samples, and you will just count the transition. You will just count the transition from one state to another. Okay, for example, there is a transition from 1 to 0. This transition occurred one time, and then you have 0 to 0, etc. You will just count the transition. You will normalize in order to have probability distribution, and you will just put this on inside the graph in order to try to approximate the unknown truth value of the Markov chain just by seeing one of its sample. So this was for the classical approach. The classical approach was shown to be minimax optimal. It means that if you have a length of the sample infinite, you are sure to have the exact to recover the exact Markov chain. Another thing you can do with LLM, another method, is that you consider the same problem, but you input the samples to the LLM and you check out the output, and you put the output in the arrows. So this is basically the in-context learning task that we observed on the first figure and on the previous table. Right, so yeah, you can just prompt your LLM and you will check what probability it puts on each state of the chain. Okay, so we will consider this task in the following of the paper, and the idea is that by just putting some mathematical setup, you consider Markov chain of D state. In the previous example, there were just 3 states, so 0, 1, 2. So you consider Markov chain of D state. You consider that you have access to n ICL samples, and just by denoting the sequence of the n first sample as S, and by denoting the mixing time of S as Tmin, the mixing time of a Markov chain is just some characteristic, it's just a characteristic parameter that you have on your Markov chain. You can derive this kind of bound. You can bound your test error with high probability by 2 terms, by a sum of 2 terms. First, a distribution shift. Which will tell you, basically, if your model has been trained exactly on this sample, obviously this term will vanish. But if there is a kind of gap, if it has not been in the training distribution, in the training set, this term can be non-zero, and the other term, more importantly, varies like this. So you have this mixing time times the logarithm of the number of states, and this is very important. We will see why later. And as we have seen, a classical square root of n on the denominator, right? So after deriving this theorem, we are like, okay, now let's just see on LLMs if it works, if it follows this law. And the idea is that we took a lot of LLMs, some recent LLMs or some quite old LLM, and we realized that yes, it follows the law given by the bound. Also, we also considered randomly generated Markov chain that we prompt in order to make sure that this Markov chain has not been seen during training. So there is a real generalization property here. So also, yeah, you can see the dependence, and you can see that the most recent model stay much closer to the bound. So there are less distribution shift. They seem to be more able to generalize. And yeah, for example, you know that GMA2 is, I think, was released late 2023 or early 2024, and the other model was a bit old. So yeah, as you can see, you can really check that on the result. Okay, the other term was the mixing time, and we wanted to see if it really acts like this. So the idea is that we also plot the error as a function of n, as previously, and what you can just see is that the more the mixing time is high, the more it will be difficult to decrease, and after the n ICL term will just be higher. So at the end, they will just have the same rate. But there is really something with mixing time. And if you plot the same error with another scale with a ratio, basically, you will clearly see the scaling law given by the theorem, because remember you have something like square root of t mean on an ICL. So if you use this ratio, you will clearly see this with the value of t mean now. Yeah. So the last term that we wanted to check is this term. So the logarithm of d. So remember when I talked about this frequentist approach, I told you that this is a minimax optimal approach. But the theoretical bound for this approach is something like square root of d over NICL, in contrast to our log of d over NICL with the square root. So it means that for high value of d, the frequentist approach can struggle, even if it's minimax optimal. But the LLM approach is in log of d. So for high value of d, we can expect that, okay, it performs pretty well. And okay, on the left, we prompted, we used the two approaches with a 3-state with d equals 3 with 3-state Markov chain, and as you can see, it is roughly the same when NICL is high. But if you consider, for example, a Markov chain of a huge number of states, so 700, for example, in this case, of d equals 700, we will say that the fact that the first bound is in square root of d over NICL, like the NICL doesn't have the time like we struggle for small value, you will see that the frequentist bound in purple will just struggle. Whereas the other bound, it will be like just showing 10 example, it will decrease and it will be quite close to the tendency. So yeah, that's also another thing that shows that okay, our bond is really express what happened in practice. And yeah, so this was really important because we really our initial goal was okay to derive the theoretical result that explain what happened in practice, right? So this is basically the end. I will just do a 3-point recap. So the first thing that we have done is that we have given an explicit characterization of like the inference mechanism of an LLM by during connection with finite state Markov chain. So if you can check in the paper if you want really formal definition, but yeah, you really can express your Markov chain, your LLM as a Markov chain. We have derived a lot of theoretical insight, post-stationary distribution, generation bound, sample complexity, and what happened during in-context learning. And we also have checked this particular the in-context learning bound on recent LLMs and show that this bound can address this practical problem. All right, so thank you for your attention. If you have any questions, feel free to ask, and thank you.
Yeah, thank you very much. Thank you. Any questions or comments? Yeah, so maybe like a question, like what do you see as the limits of this approach of LLMs as Markov chains? I mean, do you think that this is like a global point of view where we can say that LLMs are Markov chains, or is there you think there is more in LLMs than Markov chains?
No, basically we can really characterize LLM as Markov chain. So you really can do an explicit connection between both. Yeah, so as you can check, like if you consider two sequences of length up to k, you can say, okay, if my sequences are aligned, there's a zero probability to transition between them, and otherwise there is the probability output by the softmax of the LLMs. Like we have a really explicit characterization, verified characterization, and the ID just says, okay, those machines are really impressive. You can do a lot of things with them, but they just act like Markov chains. Like they are nothing more than highly sophisticated Markov chains, and they have the same limit as Markov chains, in the sense that they have stationary distribution, they have this kind of model collapse, they have all those things. And as you may know, there are other efforts to modelize language through different models, for example, state-based model, or more another approach was RNNs. So basically, state-based models are inspired from them, and those models they do not implement what I talked about before, the context window phenomenon. They don't implement this in an explicit manner. Like you don't have an explicit number, for example, for GPT-3, it was this number. In this kind of model, you don't have this. This is more implicit. And that's why, in my opinion, I believe that, okay, if we shift from, if we shift on those models, it can be better. Like we are out of the Markov chain connection.
Okay, so maybe like another question. I mean, there was like another approach, which is like in a way looking at LLMs as the diffusion models. I mean, do you see? Because I mean, diffusion models, I mean, are not necessarily Markovian. So in a way, how do you see the connection with diffusion models from your point of view?
So the thing is that when you modelize Markov chain, LLM as a Markov chain, like you are saying, okay, the LLM is this precise Markov chain, and if you consider diffusion process as the fact that they are just basically Markov processes, so those are a kind of Markov processes, but I'm not sure if you can say that this Markov chain is a diffusion process. Also, the fact that it occurs in a discrete with discrete timestamp. You know that diffusion model is like continuous flow. It in discrete state space, not in continuous state space. For example, if you generate an image, the value of the pixel, you know, is in a continuous scale. And here, if you shift from one word to another, there is a discrete gap. So I think those are really two different approaches, and there are no real link between this Markov chain, this Markov chain that describes the LLM, and the Markov processes that we consider while doing diffusion.
Okay, so yeah, so this was I was trying to see if you consider the discretization of the diffusion model.
But yeah.
So, but I'm just guessing. So I'm just trying to see if
Yeah.
you thought
So
about.
yeah, so by doing this, you have to consider the continuous time Markov chain and to consider the discretization of this continuous time Markov chain. Yeah, I haven't thought about this, but yeah, it could be interesting.
Okay,
Could be
okay, yeah.
interesting.
Just a thought because
Yeah.
I'm just like aware of these two kind of approaches to looking at LLMs from either your approach as Markov chains or the other one as diffusion models.
Yeah.
And I'm just wondering
Okay. Yeah.
if there is a link. Yeah. Anyway, it's something we can think about. Yeah.
Can you consider non-Markovian?
Sorry.
Can you consider a situation
What?
that
Yes.
non-Markovian is happening, And I will connect it to the other issue of ergodic or non-ergodic. And that could be like in the training, we make assumption that things are Markov chain or Markovianity, but
Yeah.
it could be that this assumption doesn't hold every time.
Okay. So are you talking about the data, or are you talking about the model itself? Because if you talk about the model itself, this is not an assumption. This is clear. This is just an assumption. This is how the model works. The model is a Markov chain. Like you can really explicitly derive data, like explicitly characterize an LLM as a Markov chain. On the other hand, if you talk about the data that in this like in the experiment, like of course in our experiment we just said, okay, our dynamical system that we will prompt to our LLM is a Markov chain, but of course you can consider non-Markovian data, or for example, yeah, just a natural language data, for example, Turkey, but I mean you can say, okay, this is a Markov chain, like, you know.
So if the data is non-Markovian,
Yeah.
in some cases, the
Yeah.
model that assumes Markov chain is we have to look for alternative, no?
Yeah. So if the data are not Markovian, so in this experiment, like we were not able to derive this, for example, yeah, because here we are clearly doing the hypothesis that the data during inconstruction are Markovian. So you can do work, like you can, I don't know, do another assumption, or just correlate the data, or something like that, and you will perhaps be able to derive other bound. In this experiment setup, we really did this because we have some kind of control on the data that we infer to the LLM. But on the other hand, if you remember, when I presented the pre-training bound, the bound related to pre-training, just there, when I presented the bound related to pre-training, we are not saying that the pre-training data are Markovian. We are saying that they are dependent. There's some kind of dependency between this random variable, not necessarily Markovian, not necessarily IIG. Like it can be anything, and this is reflected by this coupling, which appears in the bond. So yeah, if you talk about the ICL stuff, okay, you're right. This is a constraint setup by considering Markov chain, but you know, in the training result, this is the more general assumption that you can make.
So the lesson is very simple. We have to be very careful when we use any data with certain model. But thank you very much for this detailed talk. I appreciate it.
Okay, thank you. Thank you for your question.
All right,
Welcome.
thanks. Yeah, thank you. Any other questions or comments? All right, seems not. Yeah, thank you very much, Oussama, and thanks everyone for coming. And yeah,
Thank you.
yeah, thanks
Thank you
again.
so much. Bye.
Yeah, bye, everyone. Bye.
Bye. Thank you.